You've probably heard the term weather bomb on the news, and it sounds like something straight out of a disaster movie. While the name is dramatic, it's rooted in a very real, very powerful atmospheric phenomenon known as explosive cyclogenesis. These storms can unleash hurricane-force winds and torrential downpours with very little warning, and today we're going to dive into the science behind them. Welcome to G Fun Facts Online. A weather bomb, or as meteorologists sometimes call it, a bomb cyclone, isn't defined by its size, but by the incredible speed of its intensification. For a storm to earn this ominous title, its central atmospheric pressure must plummet by at least 24 millibars in just 24 hours. To put that in perspective, a standard barometer might only change a few millibars over an entire day of calm weather. This rapid pressure drop is the engine of the storm. It creates a powerful vacuum effect, causing surrounding air to rush inward at ferocious speeds, which we experience as destructive wind. It's crucial to understand that these are not hurricanes. While both are powerful low-pressure systems, they get their energy from different sources. Tropical cyclones, like hurricanes, are warm core storms that form over warm tropical waters, fueled by the heat and moisture rising from the ocean. Bomb cyclones, on the other hand, are cold core storms. They are born from the clash of different air masses in the mid-latitudes, typically during the fall, winter, and spring. So, what is the precise recipe for one of these meteorological bombs? The formation is a complex interplay of several atmospheric ingredients that must align perfectly. At its heart, explosive cyclogenesis begins with the interaction between two contrasting air masses. One is cold and dry, the other is warm and moist. The boundary where these two masses meet is called a front. When the cold air mass aggressively plows into the warm air, the warmer, less dense air is forced to rise. This upward movement is the first critical step in creating a low-pressure system. As that warm, moist air ascends, it cools, and the water vapor within it condenses, forming clouds. This condensation process releases a tremendous amount of energy known as latent heat, which acts like a booster shot, further fueling the storm's development. However, the most critical ingredient is high above us in the atmosphere, the jet stream. Think of the jet stream as a high-altitude river of fast-flowing air, often exceeding 200 kilometers per hour, meandering across the globe. For a bomb cyclone to form, an area of low pressure at the surface needs to be positioned directly under an area of divergence in the upper-level jet stream. This divergence is a region where the air in the jet stream is spreading apart, and it acts like a powerful vacuum, pulling air up from the surface storm below. This suction from above is what causes the surface pressure to drop so explosively. Within the jet stream, there are even faster corridors of air called jet streaks. If a developing surface low moves into a sweet spot relative to one of these jet streaks, specifically the left exit or right entrance region, the divergence is enhanced, and the storm can undergo its most explosive intensification. The physics behind this intensification is a process called baroclinic instability. This instability arises where there's a strong horizontal temperature difference. This temperature gradient creates potential energy in the atmosphere, and the developing cyclone is the mechanism that converts that potential energy into the kinetic energy of motion. In other words, violent winds. The final ingredient is fuel, and the best fuel source is a warm ocean. The world's most active regions for explosive cyclogenesis are found over warm ocean currents, like the Gulf Stream in the North Atlantic and the Kuroshio Current in the Northwest Pacific. These currents provide a near-endless source of heat and moisture. The stark temperature difference between the cold air coming off the continent and the warm, moist air over these currents creates a highly unstable, or baroclinic, environment, ripe for storm development. So what does a mature weather bomb look like, and what can it do? On satellite imagery, it's a formidable sight, often displaying a characteristic comma-shaped cloud pattern. The head of the comma is where you'll find the most intense precipitation and the strongest winds. The rapid pressure drop creates an incredibly steep pressure gradient, which generates winds comparable to a Category 1 or even a Category 2 hurricane. These winds can cause widespread damage to buildings, topple countless trees, and bring down power grids. Bomb cyclones are also prolific producers of precipitation, but the type depends on the temperature. In the warmer part of the storm, you can expect torrential rainfall, leading to widespread flooding. In the colder sectors, a bomb cyclone can produce heavy snowfall and strong winds, creating full-blown blizzard conditions with zero visibility. And sometimes, you get the most dangerous scenario, a layer of warm air aloft with sub-freezing temperatures at the surface. This causes precipitation to fall as freezing rain, coating everything in a thick, heavy layer of ice. This makes travel impossible and can lead to widespread power outages as ice-laden tree branches and power lines snap under the weight. A difference of just 1 degree can be the deciding factor between rain, snow, or a dangerous icy mix, making it a huge challenge for forecasters. For coastal areas, the threat is amplified. The storm's low pressure and powerful onshore winds can create a significant storm surge, an abnormal rise in sea level that can cause severe coastal flooding, especially if it coincides with high tide. History is filled with examples of these devastating storms. One of the most famous is the Great Storm of 1987, which struck the United Kingdom. It is infamous partly because some weather reports failed to predict its severity. A BBC forecaster famously said not to worry. But overnight, the storm underwent explosive cyclogenesis and slammed into southern England with gusts up to 100 miles per hour. It caused immense devastation, downing an estimated 15 million trees. Then there's the perfect storm of 1991, which inspired a best-selling book and a Hollywood movie. This was an incredibly complex system, formed from the merger of a cyclone with the remnants of Hurricane Grace off the coast of North America. The storm's most significant impact was the generation of massive waves, with some rogue waves estimated to be as high as 100 feet. It was this storm that tragically sank the sword-fishing boat Andrea Gale, with the loss of its 6-person crew. More recently, in January 2018, a powerful bomb cyclone brought blizzard conditions to the east coasts of the United States and Canada. This storm's central pressure dropped an incredible 53 millibars in just 21 hours. It brought heavy snow to regions as far south as Florida and Georgia, and in Boston it produced hurricane-force wind gusts and a record-breaking storm tide that flooded parts of the financial district. Predicting the formation and rapid intensification of these storms is a major challenge, but our capabilities have improved dramatically. Modern weather forecasting relies on numerical weather prediction models. These are complex computer simulations that use the fundamental equations of atmospheric physics to forecast the future state of the atmosphere. Global models like the American GFS and the European ECMWF are crucial for predicting the large-scale patterns that lead to explosive cyclogenesis. Alongside these models, satellite imagery is an indispensable tool. Satellites provide a continuous, real-time view of a storm's development, revealing its characteristic comma shape and other features like the dry slot, an intrusion of sinking dry air that can further intensify the storm. A pressing question is how climate change will affect the frequency and intensity of these storms. While the science is still evolving, there is growing evidence that a warming world could lead to more intense cyclones. Warmer oceans provide more fuel in the form of heat and moisture, which could supercharge these storms. Some climate models suggest that while the overall number of mid-latitude cyclones might decrease, the number of the most intense storms, the bombs, could actually increase. A significant concern is the potential for more frequent compound events, where a bomb cyclone occurs in conjunction with other extreme weather, like an atmospheric river, a narrow corridor of concentrated moisture. This is exactly what happened in the Pacific Northwest in October 2021. A powerful bomb cyclone, one of the most intense ever recorded in the region, combined with a potent atmospheric river, leading to both devastating winds and catastrophic rainfall and flooding. Given their destructive potential, it's crucial to be prepared. The first line of defense is simply to stay informed. Pay close attention to weather forecasts and heed all warnings issued by meteorological services. At home, prepare for the high winds by securing any outdoor objects that could be blown around, like patio furniture or garbage cans. Clear your gutters to help prevent flooding from heavy rain. And always have a well-stocked emergency kit with flashlights, batteries, and a first aid kit, ready for potential power outages. If you live in a low-lying coastal area vulnerable to storm surge, know your evacuation routes and be ready to leave if authorities give the order. Weather bombs are a stark reminder of the immense power of our atmosphere. They are a complex and fascinating phenomenon, born from a precise and powerful dance of air, water, and energy. As our understanding grows, so does our ability to forecast these dangers. But in a world with a changing climate, the threat posed by these and other extreme weather events is likely to grow. Investing in science, improving our forecasts, and preparing our communities is the best way we can weather the storms that lie ahead. Thanks for tuning in to G Fun Facts Online.